Welcome back. This is the second part in this series, and my goal is to show you how some of the mathematical formulations we derived as part of the curve fitting exercise could be easily explained when we start to use probability first approach to our modeling. Before that, here is a quick recap of what happened in part 1. We made a hypothesis that a linear model of a certain polynomial degree would be able to capture the underlying function of our dataset. In order to determine the weights, we used the sum squared error function and saw that there is an analytical solution for that. In simple words, given a design matrix X and target vector T, you can get the weights. Then we saw that a more capable model, that is the one with more weights, a higher order polynomial, overfitted. It worked really well on trained data points but failed on test data points. Our first remedy was to increase the trained data set, and it did work. But then we made it work on limited data set as well with the help of ridge regression, which introduced a regularization or a shrinkage of weights to avoid overfitting. We also had the formulation of how given a weight vector that we found using regression to make predictions. The symbol T with a hat on it represents the prediction. In this case, it is a vector of predictions. Recall that I am using bold lowercase letter with orange color for vectors and bold uppercase letters with blue color for matrices. Now, this target variable is going to be one of the characters in this tutorial today. As such, getting the target variable is the end goal of any modeling exercise. That is to predict the output or target given the new data. That said, here is a thought, which for the lack of better word is the soul of our tutorial today. Given a model and its weights, how sure we can be about the value of the prediction? But what does it mean to be sure? You see, the value of the prediction here, that is T with a hat, is a vector of point estimates. That is, it does not possess any other information that could tell us how to quantify our confidence in it. This is a moment when we have to be very honest with ourselves regarding the whole modeling and process of finding the unknowns and the predictions they make. The fact remains true even today that our models are not that powerful when it comes to capturing all the sophistication and complexity of our physical world and the processes it has. Don't get me wrong, these objects and techniques are helpful, but we should always be suspicious of them. Being suspicious here is valid because more than often we do not have access to good and large datasets. We are limited by our mathematics for modeling, and even if we could perfectly model them, quite often computational resources become the limiting factor. So what could help us here? You see, whenever we have a suspicion or uncertainty, it is the probability theory that plays a key role to help us out. So if we were to treat our target variables as random variables, maybe there is a way out. A random variable has a distribution, that is, it can attain different values or states, and more importantly, these states have an associated probability. In the previous tutorial, we had 10 data points. So we can say that we have 10 random variables. And this, by the way, is the end of the role of the vector T with a hat on it for the rest of our tutorial. His role has ended for now because we are going to look at our problem from a different viewpoint. Instead of seeing target variables as scalar values, we are now going to treat them as random variables. And from that, find answers that will give us the prediction with uncertainty quantification. The central characters in this story today are indeed these random variables that correspond to the target variables of our model. And this formulation should make us think about various questions and scenarios. For example, which distribution type these random variables follow? Here, type could be discrete or continuous, or maybe even a specific distribution type. For example, is it Gaussian, is it student, binomial, and many other types of distributions. Do all the target variables here follow the same distribution type? I think it is fair to ask this as well. And finally, a more natural thought would be about the parameters of the distributions. Let's say that they all have the same distribution type, but do they share the parameters, or do they have their respective parameter values? The first one is easy. That is, it depends on your problem. You either will figure it out using your data, or as we usually do, we will make a bet on the distribution that comes closest to our dataset. As such, there are hundreds of distribution types that are defined, yet we work with a very limited subset because quite many times computational capacity also influences our decisions to select the distribution type. Moving on, do they follow the same distribution type? Well, quite often, yes. But do not ignore processes where there is a sort of a switch point and outputs change with time or during certain phases. But for now, perfectly okay to assume the same distribution type. The third question is interesting. Yes, they have their respective parameters, but they may share the parameter as well. Sharing most likely would simplify the mathematics and computational aspects, but then will take us a bit more away from reality. I hope you appreciate that we always strive to achieve a balance between approximation and computational requirements. If you aim to get the most perfect model in terms of accuracy, and to meet that, if it requires a lot of computation, it is likely that you will have problems with deployment and, more importantly, user experience. Unlike software engineering, in this field, we accept approximation. I'm preaching this, but honestly, it is still very hard for me to accept approximations. I guess I'll always be the software engineer first. Oh, there is one more. How do we determine the parameters of the distribution? Well, that is the main topic of this tutorial. Especially since we are now seeing our target variables as random variables, we better find the parameters of the distributions that these random variables follow. One more. You have met this guy before. All he does is ask questions. Now he is asking, how can we be sure about the parameters of the distributions? This is a very good question indeed. Remember, earlier I emphasized that when it comes to modeling, we ought to have suspicions, and therefore we should apply the same rules to the parameters of our random variables as well. More on this in the next tutorial. For now, we gave our full attention to target variables and aim to do uncertainty quantification only for them. That said, we start with modeling and we make some assumptions. We assume that all these random variables here follow Gaussian distribution and they are independent of each other. All these random variables are going to have same variance. In other words, they would be sharing the variance parameter. Now, these assumptions should raise some eyebrows, and rightly so. Are there some justification to these assumptions? Well, there are. They are not completely absurd, and I will explain them at one point during the series, but not today. For now, you would have to trust me on these assumptions. Here is a plot that should help solidify our random variable formulation or intuition so far. Essentially here the target variable, which is a point on this function, the red curve, has a distribution. The distribution here is indicated using the normal distribution, the blue plot. So in a way the target value is the mean value and the distribution function is showing the other possible realizations of this target variable. With that said, we are ready to start assigning symbols and representations to our dear target random variables. Here, this stylish looking n is the symbol for Gaussian distribution, as it is also called normal distribution. A normal distribution has two parameters, the mu and the sigma squared. Mu is generally used to represent the mean value, but in the case of the normal distribution, mode and mean are the same. Mode means the largest value. This sigma squared is called variance. Sigma by itself, that is without the square, is the standard deviation. Usage of both standard deviation and variance is common. The rest of our target variables follow the same symbols, except notice that all of them share the same variance, but they all have their respective mu parameter. Now, in the book, instead of variance or standard deviation, a third term is used, which is called precision, indicated here using the symbol beta. Precision and variance are related to each other, as I am showing here. The significance of the usage of precision will be revealed in later tutorials. For now, just see it as an alternative notation, and that should be good enough. We can now do it for the rest of the target variables as well. So, in summary, after seeing the target variables as random variables, our task is to find their mu parameters and the precision parameter that is shared between them. Now we make a hypothesis to use a polynomial to model the mu. If you recall from the part 1 where we directly predicted the target variables using the polynomial, here instead we are predicting or estimating the mu. The approach is more or less the same. See that as well. Essentially the curve that you see represents the mu or the mean values. Or we can say that the polynomial will give us the mean value of the target variable. We also start to see the random variable as a conditional probability distribution. It is conditioned on x, the independent variable, w, the weights vector of our linear model, and the parameter, which is a precision, which tells us how close or far the realized value of random variable is from its mean value. Thanks to the linear model for the value of mu, we can now write our formulation of distribution in this form as well. Essentially, I have replaced mu with the function, with the linear function of the weights. And we can do the same thing for the rest of the variables as well. And this is the final form that we will use to represent our target random variables. And it also brings us to the most important question that we would ask ourselves in order to find the unknowns in this formulation. That is the weight vectors w and the precision beta. And that question is, what values of w and beta will give us the maximum joint probability of these random variables? Here is a quick reminder of how we calculate joint probability of two events, let's say A and B. To calculate joint probability, you multiply the probabilities, and one of the factors would be the conditional probability. Now, if two events are independent of each other, then it is the product of their marginal probabilities. And since we have assumed that our target variables are independent, we can simply multiply them like this. This is a more concise form of representing the above product of target random variables. This pi looking symbol represents multiplication, and it also displays the number of terms being multiplied. This formulation is also called likelihood or joint likelihood for the target variable. The symbol used is still P, but you would also see a symbol L instead of P whenever we talk about likelihood. Likelihood and probability distributions differ from each other, as probability distribution has an additional requirement of being normalized. And also you can always interpret likelihood in the context of target variables that are conditioned on the parameters. That said, the most important issue in this formulation is that we do not like products or multiplications in machine learning. You see, the terms being multiplied will often be small numbers, and your computer may round them to 0, resulting in the entire right hand side here becoming 0. Number issue, we generally operate with logs, and hence we are interested in log likelihood instead of likelihood. How the log likelihood of one random variable looks like, and from there we can infer the log likelihood of the product of multiple random variables. This is a function describing the normal or the Gaussian distribution. This is how it looks if you have never seen it before. Now I take the log of it, and this converts multiplication into addition. Log and exponential terms cancel each other in the second term. And now I further split the first term, and this is the final simplification. The log of 1 is 0, and this is the reason we get this formulation. Since we are using precision instead of variance, we can see the log likelihood in terms of precision as well. And here all I have done is to move the terms around and nothing more. So this is how the log likelihood for one random variable looks like. And when we compute it on the product of multiple random variables, it would translate to something like this. And more importantly, you can see that this first term in the log likelihood looks very familiar. This is the sum squared error function that we had in the part 1. The most important thing is I did not have to explain you why we are squaring it and why there is a multiplication with half as I did in part 1. It simply was the outcome of taking the log. This means that there is a connection here between the linear regression and the maximum likelihood estimation. More on this in few minutes. One more mod we need to make to our log likelihood formulation is that we put a negative sign in front of it. Because of this, I have adjusted the right hand side as well. We do this because now we can use the minimization procedure to find the stationary point. Instead of maximizing the log likelihood, we do the minimization of negative log likelihood. The outcome is going to be identical. It's just that the minimization is the default process that many libraries in machine learning implement. 2 steps. First, minimize with respect to the weight vector, and then minimize with respect to the precision parameter. The second term and the third term do not have w's in them. When we minimize with respect to the weight vector, we can cancel them. They will just go away, and we can see that the solution is identical to what we got for linear regression. Only difference is that I'm using W subscript ML instead of W star. We minimize with respect to precision. This time around only third term will be deleted because it does not have beta in it, and this is the function we will get. In this function, we will put the value of the weights that we obtained in the previous step, and we will get our precision. In summary, for finding both the unknowns, that is the W and the beta, we have analytical solutions. This also means that the weight vector would be the same as we had in part 1 of the series, which means that the mean of the distribution will be given by our linear model. This formulation, by the way, is now called predictive distribution. That said, at the end of the day, you will have to select a point estimate value. And one choice for that is that you can choose the mean value here. In normal distribution, mean and mode are the same. We will revisit this suggestion that I have given you in the later tutorials because a lot of the Bayesian thinking is around how do you get the final point estimate. But for now, I am suggesting that the only thing you do is to just use the mean value that you get from your linear model as the final prediction. But this raises an interesting thought. If you use mean as the final predicted value, the prediction is identical to what we got in the part 1. And you would be right. But then you should challenge me why we went through this whole thing if prediction was going to be the same. And the reason for that is that you have to stop thinking only about the value of the prediction. Let me summarize what you learned by going through this process. First, even if you have the same prediction value from the part 1, where we did the traditional vanilla linear regression explanation, you now have an extra information about the precision, which gives you the confidence in the predicted value. You never had that. You learned how to think in terms of probabilistic modeling. Our approach was very different from that of a part 1. Well, to be honest, it would be a big claim to say that we learned probabilistic modeling, as we have merely taken the very first baby step in that direction. Nevertheless, we have started to think in that direction. And finally, you saw how naturally the error function emerged because of how we framed our model and worked towards a solution. Unlike part 1, I did not have to give you any reason for doing a squaring and or multiplication by half. The mathematics naturally led towards the same solution when we assumed the Gaussian noise. Fine, I did not say anything about this Gaussian noise. So one last thing is, let's say that in this formulation of negative log likelihood, if we assume the beta, that is the precision, to be 1, you can see that the second term will be 0 because log of 1 is 0. And when you will do the gradient, take the gradient of this function, the third term will also vanish because there is no beta or w in it. And note that in the first term, now the factor is exactly half. This is identical now to the sum squared error function when we assume beta to be 1. In other books and literature, this whole thing is expressed in yet another alternative form. Here is our old friend, the linear model, but this time note that it has this extra term in it and a symbol with a symbol called epsilon. This epsilon is your Gaussian noise. As such, this is a more correct form of model specification that could have been used in part 1, but I didn't want to confuse you at that time by bringing the distributions in the mix. Hope this clarifies the notion of Gaussian noise, which is assumed when you are doing your traditional linear regression. This brings us to the end of this tutorial. The most important takeaway here is to think of your target variables as random variables, as thinking in this direction enables us to get the uncertainty associated with it and helps us move away from point estimate to predictive distribution. And also linear regression and some squared error function is just a special case of maximum likelihood estimation when we assume Gaussian noise. With this, I want to thank you for the precious time you spent here. Hope this tutorial was helpful. Let me know if you have questions, comments, feedback, and I would be happy to answer them. Bye bye for now. See you next time.